Okay, in last week's lectures, what we were looking at was we were looking at a plate. Now, we could have equally been looking at a rod or a three-dimensional object. And what we were doing is we were finding the steady state temperature distribution. The steady state temperature distribution satisfies an equation known as Laplace's equation. And what we're going to do now is we're going to derive the equation for the transient state temperature. So now we're only going to do it for a rod, but it generalizes easily to the case of a plate. So suppose that we have a plate with boundary temperature distribution given, and we know that the steady state, say the plate begins at temperature 0. We know that if the boundary temperature, say, is larger than 0 on average or whatever, we know that the heat is going to flow from the boundary into the plate, and the temperature of the plate is going to rise. And it's going to keep on rising until you get to an equilibrium, which we'll see below. And at that point, that's the steady state temperature. Now, what we're going to do in this section is derive what's called the heat equation, which says it's basically a differential equation that describes the temperature not just as a function of position, which would be but also as a function of time. Okay, we're just going to do it for a 1D rod though. Okay, so imagine a 1D thin rod. Now the reason that we take a thin rod is that we want it to be such that, like, if the rod is actually quite thick, then, and this is going to be an insulated one, I'm not sure exactly what happens with the temperature. Is the temperature on the outside warmer, temperature on the inside warmer? I suppose it depends on if it's insulated or not, but we'll just imagine that the rod is so thin that it actually doesn't really make much of a difference. Now we'll take the rod here to be actually a square rod. Now it doesn't really matter, you can rewrite all of this using different coordinates and you get a similar story. So here's the rod. Now at the moment we're saying that it's insulated except perhaps at the end. So there's some kind of temperature here, we'll call it. Now actually I think you can have the temperature changing in time, but we'll just have it constant. So we'll have the temperature 0 here fixed, and the temperature here at the L being the length of it, let this be fixed as well. But otherwise there's no heat loss between the rod and the thing. Now this thing is three-dimensional. I haven't quite drawn it like that, and I've actually exaggerated the dimensions. I've made it quite thin, but imagine it even thinner. Now what we would have looked at in the previous section was if you take a little volume element of this, so just chop off a little piece and just consider a little volume element. So this thing, a little bit of the rod. Now the idea that the rod is thin means that you don't have to chop up that just chopping like this for a small delta x, that the other so okay, what are our directions? I think we're talking delta y, excuse me, x direction, y direction, z direction. I'm saying that if you chop the piece of rod into a piece of length delta x, that automatically the dimensions of the rod are such that delta y and delta z are very small as well. Okay, so this is a zoomed in version of this, and so this would be delta x, this would be delta y, and this would be delta z. So in steady state, what we would have looked at previously, it's quite easy to analyze it. The heat into the element in unit time, delta T, equals the heat out. And where Q of x, which was this heat flux density vector that we mentioned the last day, so Q would be kind of, so the heat flow here, certainly in this direction, the heat flow would be like Q of x. I can talk about times I hat if I want, but something like that. So you got heat in, that's how much goes in there, and then so actually that x is the point there, and then x plus h, or excuse me, x plus delta x here, and then you've got heat flow out, x plus delta x times I. And then this is a density thing, so you multiply by the unit time as such, and you multiply by the area and you get the right thing. Now looking at this, I think there's possibly a delta t missing here. Now it's saying unit time delta t, that's not great. I can just throw in an extra delta t, it doesn't make much odds. So this is how much flows per area per time. So multiply by the area and the time, and then you get the heat flow out. Okay, divide both sides by delta V times delta T and manipulate it into this form. As the piece of volume gets smaller and smaller and smaller, this approximation becomes more and more accurate, and you end up with, if the volume is getting small, then the delta X is getting small. You're left with limit, what's going on with the green here, delta X will have to go to 0 necessarily. Q of X plus delta X minus Q of X divided by delta X, and this, at this stage, you should recognize that this is a derivative. Now, it is a partial derivative. Now, it's probably be a bit more careful to make that be the case, but we'll just take my word for it here. So this is delta Q, delta X. And I think just for what's going on in the next bit, this can be called QX. That may or may not be the notation you've seen in your maths class. Then you use, so this is saying that, this is, I don't know what you'd call this. This is the derivative of the heat flux density, this thing. And Fourier's law says that, what's going on here? It's a, I think this is not QX, so this should be Q of X. And while you could call this QX, I don't really care about that. So Q of X is minus K times the derivative of temperature. So if you write the partial derivative of Q of X is the same as the partial derivative of this with respect to X, you should end up with, now this is equal to 0, by the way. So using Fourier's law, you get that the partial derivative of Q with respect to X, which is equal to 0 by this, but is equal to the partial derivative of this by Fourier's law. Fourier's law says that the heat flux density is proportional to the rate of change of temperature. So it's, well, this is, well, it's the temperature gradient. So basically it says if the temperature change across the rod is large, like say cold, hot, then the heat flux density will be large as well. That makes sense. When there's differences in temperature, you get flow of heat energy. So this should be the same as minus K partial T partial X, fix the constant, minus K, and then the partial derivative respect to X of the partial derivative T respect to X will be the second partial derivative. And remember, this is equal to 0. We get the one-dimensional Laplace equation, which we would have looked at the last day. Well, previously. Okay. So this this is steady state temperature differential equation. Now remember, the rod is thin, but insulated is the big story. Now if you've got boundary conditions, say T0 and T1, it's the solution is pretty easy. So I'm going to ask you in a moment to think about a function that has a second derivative of 0. Like you can kind of arse around here and say, what about the y and z? But don't worry about that. What has a second derivative of 0? And if you're thinking back to stuff that we did with Euler's method, etc., you should know that this is a line. Okay, so if the boundary temperatures are T0 and T1, we know that the temperature goes from T0 to T1 and it's a line. So you can actually solve this exactly. So let's say we have temperature 0 here, and say this is L and this is temperature 1. The temperature of the rod goes like this. Okay, so very, very simple behavior. And is this something that I would have known? I'm not sure I would. So basically it says that if you're in steady state, as you move along the rod, the change in temperature is pretty much uniform. It's constant. Maybe we'll just fill in a few dots here. So it's saying that the change in temperature with respect to distance, so like if you travel along by 1 and travel along by 1 here, the change in temperature is the same, is a constant. We'll just call it C. And then now we won't worry about it being a partial derivative, but if you anti-differentiate both sides, in fact I should use the symbol M here, you can go in two directions actually. Differentiate again, you get 0, which is exactly what we said was the steady state temperature. Alternatively, you could say, oh, what curve has a constant slope? Well, mx plus c. Now you should be very comfortable from Marina dealing with equations of lines. If you have the thing plotted in front of you, it's very, very easy. M is just going to be rise over run, which in this case will actually be negative because it's going down. It would be T1 minus T0, which would be negative in this case, over the run would be L. And C is where it cuts the y-axis. So actually, it's very, very easy to write down this equation. The temperature at each point is T1 minus T0 over L. That is the slope times x plus a constant, which is the temperature at x equals 0. Okay, so this is very easy actually. And why we didn't actually... So this is a very easy situation. You actually can solve it exactly. Things get more complicated in 2 dimensions because you've got a partial differential equation. That's why we would have looked at a plate. I could have equally looked at a 3-dimensional solid, but this is what we did. Okay, now there's 2 things we can do from here. And the first one is the more interesting. Suppose the rod isn't in steady state. So we had a thing going on here. So whatever the initial temperature of the rod, maybe it was 0, and then you put it in contact. So imagine here you've got a rod that was kept in a freezer, or not a freezer, maybe, I don't know, freezing water or whatever. And then suddenly you put it in contact with these 2 temperature heat sources. Obviously the rod will heat up, and it'll heat up, but eventually the temperature will steady. That's steady state. And the temperature of the rod will be this at each point along the rod. Now the question is, what we're interested in next is, okay, the rod began at a temperature of 0. I put it in contact. What was happening, say, after 5 seconds, after 10 seconds, etc.? That's the transient state. What is the temperature at each point, at each time? That's what we're interested in now, and that'll be the heat equation. Okay. So suppose that the rod isn't in steady state, but the temperature in a volume element is changing from an initial temperature distribution, which we'll write like this. Now later on we'll probably write this as we're going to use a rod. Now this extends to a plate if you really wanted to push it, but we're just going to talk about a rod. We're going to talk about the temperature being a function of distance along the beam of the rod and time. So this would be the temperature at a point x times 0. That's probably more what I want to. What we're going to get a change in temperature. We would have discussed this in depth in the derivation of the Laplace equation. You get a change in temperature when there's a net change in heat energy. So for example, it'll heat up if there more comes in than goes out, or if a little bit comes in and loads goes out of heat energy, then what you're talking about is a loss of heat energy, a reduction in temperature. All right, so this is our little delta x. So we're going to say heat in, heat out. Okay, so we're going to have heat in, heat out. And what are we going to have? Well, the difference between this will be a gain in heat. So I'm going to call this, maybe just call this Q1 and this Q0, say. And so the difference between these, and it'll actually be this one minus this one, I think. So Q0 minus Q1 is a change in heat. Now think about this. I think Like to do this module, it is not completely necessary to understand everything I'm doing here. Ultimately, we're interested in numerical methods where you want to approximate solutions of the equation. But I think for your overall engineering and for your any bit of thermal stuff that you do, you should actually be able to understand this. So if Q0 is big and Q1 is small, then you've got a lot of heat coming in and not so much coming out, so that there's a positive change in heat capacity. That'll mean that there's an increase in temperature. Similar story, if this is small and this is big, then this will be negative, and that the amount of heat energy is decreasing. Okay, heat energy is the mass by the specific heat capacity by the temperature. Mass is density by volume. C is specific heat capacity. Now, specific heat capacity is a property of the material, and if I'm correct, it's how much energy is required to, do you know what, I'm not actually 100% sure, but it's probably how much energy, energy you need to increase, it might be 1 kilogram of it by 1 degree. Now, maybe my units are a bit funny, but I think that's right. Yeah, because then you, yeah, that sounds good. Well, I'll say it doesn't matter anyway. You can check it out somewhere else. So T is the temperature. Okay. Therefore, a change in heat energy in a volume element is, now what's going on here? So M is rho V, and here the volume is delta V. That's not a change in volume, that's a little bit of volume. That's the N, that's the C. And then the change in heat energy is a change in temperature. And this is, see, here's delta V, delta X, delta Y, delta Z. There's rho, there's C, there's delta T. So our equation is heat in, which is heat flux density by area times time, minus heat out, that is the heat flux density coming out of this face, by the area by the time, is equal to the change in heat energy, which is, we just derived here. So you do a bit of messing around. In particular, you divide both sides by delta V, delta T. So the delta T's don't, this is gone, this is gone. I don't like cancelling, I'm sorry, I just can't do it. Say you divide by delta V on both sides. Delta Y is gone, delta Z is gone. You're going to have it divided by delta X here. Divide this by delta V, that's gone, that's gone. You haven't divided by delta X, so that'll be there. Dividing by delta V, that's all gone. Okay, that's gone. Rho and C are going to sit there. We're also dividing by delta T. That's going to be gone. That's going to be gone. You're going to have delta T divided by delta T. Now this is rough, but to make it more accurate, you take the limit as the volume gets small, which is, we're saying for a thin rod, the delta X gets small and the delta T gets small, and you end up with this equation. This is a derivative. Now if you look at it, it's the wrong way around because you've got the X plus H on the other side. So this is minus the derivative with respect to X of the heat flux density is equal to rho C, and then this is change in temperature over change in time. Make the change in temperature, change in time small. This is rise over run. This is a derivative. Partial T, partial temperature, partial T. Okay, the rate of change of temperature with respect to time. And isn't that what we're interested in? Because in steady state, this is equal to 0. In steady state, the temperature does not change. There is heat flow, but it's all balanced out. In steady state, this is equal to 0. We'll see this in a moment. Invoking Fourier's law again, saying that basically this is equal to minus k times the second derivative. And so you minus, you get your plus. So I'm just saying, where does this go to here? We've seen this here, that partial q partial x is minus k this yoke. So it's minus k, which is k this yoke. A good question here would be, where the hell does the rho c go? Do I have answers? No, I do not. So it obviously means that this k and this k are different things. It's no big deal. Maybe we'll just call this thing k prime. So if you want to, just that they're different things. I don't know exactly what they are, I'll be quite honest with you, but it doesn't actually matter because you can just divide out the constant anyway. Right, so this is the derivation of the heat equation. Now, if you want to talk about, so okay, whoa, what's going on? So this is a relation, you got the temperature depending on distance and time, and it's a relationship between the second derivative of temperature with respect to distance, and the change in temperature with respect to time. Now there's a little bit what can we try and say here? I don't think I will. Maybe it's not a good idea. I think it's not too bad. The second derivative. All right, I want you to just think about the second derivative. So imagine at a certain instant. Yeah, this is good. Some specific instant. Think about which things have a positive second derivative. Now, I think the easiest thing for us to analyze this is to think about just a quadratic function. So think about a quadratic function. That would be like ax squared plus bx plus c. There's other things we may as well put in here. We're going to have boundary conditions. They're going to be, I think you can have them changing in time, but we'll have them fixed. So say the boundary conditions look like this. Yeah, this makes sense. So what is the second derivative of this? The first derivative is 2x plus b. The second derivative, so if I call this thing p of x, ax squared plus this, the second derivative of this is equal to 2a. And this is positive. The second derivative is positive exactly when this a is positive. And that's a plus x squared. It looks like this. So things with a positive second derivative have this u shape. And so what this equation actually tells us is that if the temperature has a u shape, which might look something like this, then this thing is positive, and then the derivative of temperature with respect to time is positive, and that means that the temperature is increasing. And what you get is that the temperature increases up to the equilibrium steady state temperature. So if the temperature looks like this, it rises, and similar story, if the temperature looks like this, then it's above the steady state. It must decrease down to it, because in this one the second derivative is negative, it's a minus x squared. And if this is negative, that means the derivative of temperature with respect to time is negative. That means that the temperature is decreasing in time. So the temperature would decrease down to the steady state. Now what we might call the steady state here, maybe let's call it T infinity. Because you know that if enough time goes by, well, maybe you don't know this, you probably have to talk about stuff like entropy and stuff. I can't really remember this stuff, but basically it will reach steady state, assuming there's no other weird things going on. Okay, so this is basically what we're talking about. Yeah, this is great. This is our heat equation. Now the problem is solving this is difficult. I don't believe you'll do it until 4th year. This is a partial differential equation. This is a difficult thing to solve. We just have some remarks here on the next page. The 2 and 3D, so this is a plate and a box. The equations are basically the same, except you add on second derivatives with respect to y and z. I think the material has to be isotropic, the same in all directions, otherwise you've got different k's. On page 87 we saw this little equation. Right now this we were studying the steady state temperature of an uninsulated rod, and I think our solutions typically, we're saying steady state, typically we're looking at stuff like maybe this. Now, because this is insulated, the air temperature, so this one, the air temperature has no role, and so you don't see a steady state solution like this. But if it's uninsulated and the air is cold, so let's just say it's cold, you get this kind of a shape here. Okay, now I'm just going to show you where that equation comes from. So this, how is the temperature in the rod changing with respect to time? Well, what you have here is the heat equation, which we did here, that holds, but also you've got Newton cooling. There's cooling between the rod and the air, which we're considering to be a reservoir. So you got this additional cooling term here. And then what's going on is, so you can actually even Now, I'm not sure can we solve this. It's kind of beyond what we're going to do, but so this is an interesting one where the temperature increases up to here. It doesn't quite get up to the straight line. But what's the story with steady state? Think the temperature does not change with respect to time. That's what steady state means. So steady state, when you hear steady state, you're thinking that the derivative of temperature with respect to time is equal to 0. The rate of change of temperature with respect to time is 0. The derivative is 0. It's got no slope. It's flatlined. And if this is equal to 0, and you divide out by an appropriate constant, so you have this. So this is how this works. So what we're going to do in the next video is describe, we're not going to work with this thing, describe how to approximate the solutions of this.